morning, students. In this video, we are going to start a new chapter, electric potential and capacitance. In the last few video classes, we have discussed about electric field. Do you remember? And in this video onwards, we are going to discuss about electric potential. You know, generally we use the word potential. What's the meaning of potential? For example, this boy has got potential to get a good NEET rank or JEE rank. What's the general meaning of that? Potential means capability, capacity, energy. Right? Here also, similarly, potential is related to energy. Right? And in many chapters, like in this chapter, next chapter, electromagnetic induction, then alternating currents, then like atoms chapter, and then we are having a dual nature, semiconductors. So most of the chapters we are going to talk about potential, electric potential. So very important. If you understand the idea of potential, so many chapters become very easy for us. Right? So let us discuss now. So first one, electric potential. The amount of work done in moving an unit positive charge. What's the meaning of positive charge? Unit positive charge plus 1 coulomb. So the amount of work done in bringing a unit positive charge from infinity. Infinity means where? Outside the electric field. So to a point inside the electric field. So you want to move plus 1 coulomb of charge outside the electric field into the electric field without any acceleration. Without any acceleration. No acceleration must be there. That means net force must be 0. By an external agent. That means by an external force. Against the electric field is called electric potential at point. Just now I said, without acceleration. Without acceleration means net force must be 0. Net force must be 0 means minimum we should have two forces to cancel. So one force is external force. Other force is what? Force due to electric field. Net force should be 0. Right? So the amount of work done in moving an unit positive charge from infinity to a point outside the electric field into the electric field without any acceleration by an external agent against the electric field. Against. Why? Against. So external force is applied in this direction. Electric force is in opposite direction. Net force will be 0. That's why against the electric field is called electric potential at that point. Right? It's a very simple idea. So you are having a electric field like this. Let's say in this region there is an electric field. You want to bring plus 1 coulomb of charge from infinity to a point P inside the electric field. And the amount of work done in bringing a unit positive charge from infinity to a point P is called potential at that point P. Work done to move plus 1 coulomb of charge from infinity to a point P is called potential at that point P. And this is the basic definition of electric potential. So potential is basically energy. Potential is basically work done. Work is basically energy. So literally I can say potential is nothing but energy. Potential is basically nothing but what? Energy. Right? Then electric potential due to a point charge. Electric potential due to a point
charge. So electric potential due to a point charge. Right. So for PUC exam, they might ask you this one for either 3 marks or 5 marks. Derivation is very important. It's very simple derivation. For PUC exam, 3 marks or 5 marks, and final result is very important for us. Right. What do you do? Consider a point positive charge plus Q. Around this charge, what is created? An electric field is created. Right. Now, you want to bring a charge plus Q coulombs. From where? Infinity. To where? To a point. And point P is at a distance R. Point P is at a distance R from plus Q. Okay? So you want to move plus Q coulombs of charge from infinity to point P. Right? So let us imagine this way. Let's say initially we are bringing that charge to point A. Right? And you want to move the charge from A to B. You want to move the charge from where to where? A to B. Let's say A to B is a small distance dx, and A is at a distance x. A is at what distance? X. So our aim is to find out the work done to move this plus Q coulombs of charge from infinity to a point P. Right? So consider a charge, consider a point charge plus Q at point O. Right? Now, we want to bring what? Plus Q coulombs. From where? From infinity to where? To a point P. A point P. Where is P? Inside the electric field. Right? Now, let the charge, let plus Q is at A. Let's say, let us imagine this plus Q is at this point A. Right? At point A, there is a charge, and here there is another charge. So two charges are there. So do they have any force, or there is no force between them? There is a force between them. And what is the force between them at point A? 1 by 4 pi epsilon naught capital Q into small q divided by x square. Let plus Q is at A. So what is F now? Force between the charges. So force between charges when Q is at A. So consider a point charge plus Q at point O. We want to bring plus Q coulombs from infinity to a point P. Where is P? Inside the electric field. Let initially the charge is at point A. So when it is at point A, between these two charges, there will be a force. And what is that force? 1 by 4 pi epsilon naught capital Q small q divided by x square. Is that okay? Is that clear? Right. Then, so you want to move the charge from A to B. You want to move the charge from A to B. A to B is a small distance. And what is the distance? Dx. Right? So, work done to move plus Q from A to B. Work is done against the electric field, or work is not done against the electric field. work is done against electric field because these two are positive charges, so there is a repulsive force. And this force and displacement, both of them are in which direction? Opposite. That's why against the electric field. So work done to move plus Q from A to B. So dW is equal to F bar dot dx bar. So F dx, angle between F bar and dx, both of them are in which direction? Opposite. Opposite andre theta 180. So cos 180 minus 1. Cos 180 degrees. That means here what we are going to have? Minus f dx. But what is here? 1 by 4 pi epsilon naught capital Q small q divided by x square into dx. What is this? Work done to move plus Q from A to B. So work is done against the electric field or work is done in favor of electric field? Work is done against the electric field. Right? Is that clear? Then, so work done to move plus Q from infinity to point P. From infinity to point. So, Andre, total work done we want to find out. That means total work done is equal to integration dW. Will you agree with that? And here work is done by external agent and work is done against the electric field. So, in this case or in this case, work is done by an external agent and work is done against the electric field. So, integration dW. Right? So, work done by an external agent, work done by an external agent against electric field, against the electric field. So W is equal to integration dW. Integration dW means how much we got? Minus 1 by 4 pi epsilon naught capital Q small q divided by x square into dx. So what are the limits of x? X is the distance from plus Q. Okay. What is x here? Distance from plus Q. So what is the distance between plus Q and this infinity? Infinity. So we want to move it from infinity. And we want to move the charge from where to where? Plus Q to plus P. And what is the distance between plus Q and this point P? And what is the distance R? So you want to move the charge from infinity to a point, the distance is R. So minus 1 by 4 pi epsilon naught into capital Q by small q integration 1 by x square. Integration 1 by x square means x power minus 2. So, you know the formula very well. Integration x power n dx is equal to x power n plus 1 divided by n plus 1. So, x power minus 2. And x power minus 2 plus 1 divided by minus 2 plus 1. What are the limits of x? Infinity to r. So, here minus 2 plus 1. Minus 1. Here minus minus cancel. So, I get capital Q into small q divided by 4 pi epsilon naught into 1 by x. What are the limits? Infinity to 1. So, capital Q into small q divided by 4 pi epsilon naught into 1 by r minus 1 by infinity. But what is 1 by infinity? 0. That means, what is the work done now? So 1 by 4 pi epsilon naught capital Q into small q divided by r. And what is this? This is the work done by an external agent against the electric field to move the charge from infinity to point P. Is that clear? Our derivation is very simple. Chapter name is electric potential and capacitance, right? Then, so finally what we got? Work done to move charge from infinity to point P. What is the work done? So 1 by 4 pi epsilon naught capital Q small q divided by small r. R is the distance from capital Q. And what is the amount of work done to move 1 coulomb of charge? So divide. See, for Q coulombs, what is the work done? Work done infinity p. To move plus 1 coulomb of charge, what will be the work done? W infinity p divided by small. And the work done in moving plus 1 coulomb of charge is equal to W infinity p divided by Q, and that is what we call it as potential at point P. So work done to move plus 1 coulomb from infinity to point P. Right? And what is all that work done? Potential. So is potential at point P. Is potential at point P. So potential at point P is equal to W infinity P divided by small p. But according to this equation, can you tell me what is W infinity P by small q? What you are going to get? 1 by 4 pi epsilon naught capital Q divided by small. And this is the expression for potential due to a point charge. Right? That means if you are having charge, point positive charge plus q. Right? And you want to move plus 1 coulomb of charge from infinity to a point P. And point P is at a distance r. And this work done is called as potential at point P. What do you call that work done as? Potential at point P. And the work done is called potential at point P. So BP will be equal how much now? W infinity P divided by Q, that is equal to 1 by 4 pi epsilon naught capital Q by small. So potential will be a point charge depends upon the charge and the distance. So potential at P is inversely proportional to R and directly proportional to Q. Is that clear? And here capital Q is a source charge. Small q is a test charge. Starting we have discussed. Source charge can produce electric field, whereas a test charge can experience electric field. Will you agree with that? Now see carefully. So what is SI unit of potential? SI unit of potential. Here, what's the SI unit of work done? Joule. Correct pronunciation is joule, but we will read it as joule. No problem at all. By Q, charge unit coulomb. So joule per coulomb. Joule per coulomb is called volt. What do you call that? Volt. Right? So 1 joule per coulomb is called 1 volt. So volt is written as capital V. So and this is the SI unit of potential. Right? Then potential is a scalar physical quantity or a vector physical quantity. Work done is a scalar. Charge is a scalar. So potential is also a scalar. Potential is basically work done. Work is basically energy. Energy is a scalar. Work is a scalar. So potential energy is also a scalar. So potential. What type of potential? Electric potential. So electric potential is scalar physical quantity. Scalar physical quantity. Right. So what is the dimensional formula for electric potential? So dimensional formula you want to find out. Work done. So what is the dimensional formula for work done? mLT power minus 2. Work done. What's the formula? mLT power minus 2. Work done. Work done, what's the formula? Force into displacement. So mass into acceleration displacement. What is mass dimension formula? M. Acceleration dimension formula? L power minus 2. Displacement dimension formula? L. That means what you will get? ml square t power minus 2. So ml square t power minus 2 is the dimension formula for work done. Charge. Charge, what's the dimension formula? It. But I is current or at. So that is what we are going to get. M L square t power minus 3 I power minus 1. So ml square t power minus 3 I power minus 1 is the dimension formula for electric potential. Will you agree with that? Will you agree with that? So you want to bring plus 1 coulomb of charge from infinity to a point P inside the electric field is given by a simple relation 1 by 4 pi epsilon naught capital Q divided by small r, where that is called as potential at that point. So very simple. What's the final conclusion here? If there is a charge Q and at a distance R, what is the potential? And that is given by the formula 1 by 4 pi epsilon naught Q by R. Now, previously we have taken plus, right? That means here we get plus Q. If I take here minus, here what I will get? Minus Q. So, this formula is valid both for positive charge and negative charge. So, formula is valid. So, formula is valid for both positive and negative charges. And then see 1 by 4 by epsilon naught is positive. R means distance. Distance is also positive. So V is directly proportional to capital Q. If Q is positive, potential is also positive. If Q is negative, potential also negative. If Q is 0, potential is also 0. So potential can be positive or negative, or it can be 0. So positive charge gives positive potential, positive electric potential. Negative charge gives negative potential. Negative potential. Right? So V is directly proportional to what? Q. If R is constant, V is directly proportional to Q. If Q is constant, V is inversely proportional to R. For example, if R is constant, electric potential is directly proportional to Q. Q is doubled, potential is also doubled. Q is tripled, potential also will be tripled. Q is quadrupled, potential will be increased by 4 times. Potential also will become 4 times. Q is halved, potential becomes half. Q becomes 1/4, potential also becomes 1/4. Right? That means for a given R, if you draw a graph between capital Q and potential, you will get a straight line. And if Q is constant, potential is inversely proportional to R. That means if this is R and this is potential, we are going to get a rectangular hyperbola. So as R increases, potential decreases. Of course, negative charge means negative potential. If it is a negative charge, we are going to have negative potential. Like this. This is for positive charge and this is for negative charge. Will you agree with that? Right. I hope you got some idea regarding potential. So let us discuss some more. Let us try to get exactly what's the meaning of that potential. So let me take an example. Let's say I'm having plus 1 coulomb of charge. Let's say we are having a 1 nano coulomb charge, plus 1 nano coulomb, right? So my question, at 1 meter, let's say this is point P. What is the potential? Okay, Now this is 1 meter. Let's say this is 2 meters. We call this one as M. So at N, what is the potential? Let us try to find out. So what is potential at M? So what's the formula? 1 by 4 pi epsilon naught Q by R. What's the value of 1 by 4 pi epsilon naught? 9 into 10 to the power of 9. What's the value of Q? 1 nanocoulomb. Nano into 10 to the power of minus 9. Divided by R. R value is how much? 1. That means how much you are going to get? 9 volts. So at the end, how many volts we are having now? We are having 9 volts. Similarly, find out potential at N. So 1 by 4 pi epsilon naught is 10 to the power of 9. Q value 10 to the power of minus 9. R value 2. So these two will get cancelled. That means how much you are going to get? 4.5 volts. That means here, how much you are having? 4.5 volts. Will you agree with that? Now see. Now, positive potential gives positive, positive charge gives positive potential and negative potential. How much we got here? 9 volt. Is it plus 10 or minus 9? Plus 9. This one also plus. So what is the conclusion? Positive charge gives positive potential. So positive charge. So positive charge gives positive potential. Right? Positive charge gives positive potential. And where potential is more, where potential is less. Near the positive charge, potential is more. Away from the positive charge, potential is less. That means, as we go away from positive charge, electric potential decreases. So, as we move away from positive charge, electric potential decreases. So, electric potential decreases. Right? That means which one is at high potential, which one is at low potential? Point M is at high potential, point M is at high potential, N is at low potential. Correct? So this one becomes high potential, this one becomes low potential. That means what? If this is plus 1 nanocoulomb of charge, and here let's say potential becomes 10 volts, here potential becomes 9 volts, here potential becomes 4.5 volts. As we go away at infinity, potential becomes how much? 0. Right? What is the meaning of this? You want to bring plus 1 coulomb of charge from infinity to this point. Work done is 10 joules. You want to move 1 coulomb of charge from infinity to this point. Work done is 9 joules. You want to bring plus 1 coulomb of charge from infinity to this point. What is the work done? That's 4.5 joules. 10 volts means 10 joules of work. 9 volts means 9 joules of work. 4.5 volts means 4.5 joules of work in bringing plus 1 coulomb from infinity to those points. Will you agree with that? Will you agree with that? Right. Now, if I say, instead of positive charge, let us take a negative charge. Let's say this is minus 1. If this is minus 1, potential at point M becomes minus 9 volts. Potential at point N becomes minus 4.5 volts. So this one will become minus, this one also will become minus. Another example. Correct? Use the formula 1 by 4 pi epsilon naught Q by R. What is Q? Minus 1 nanocoulomb. What is the 1 meter or 2 meters? Right? That formula 1 by 4 pi epsilon naught Q by R, generally we have derived it for positive charge, but that formula is valid for any charge. It is valid for positive charge as well as for negative charge. Now tell me, minus 9 volts, minus 4.5 volts. So negative charge gives negative potential or positive potential? Negative potential. So negative charge gives.
So negative charge gives negative potential. Right. Minus 9 is big or minus 4.5 is big? Which one is big? Minus 4.5 is bigger than minus 9. That means this is low potential, this is high potential. That means as we move away from negative charge, electric potential increase. So electric potential increase. You agree with that? So please remember, near the positive charge, high potential will be there. Away from the positive charge, low potential will be there. If you take a negative charge, near the negative charge, low potential will be there. Away from the negative charge, high potential will be there. You agree with that? You agree with that? Now, for example, here I am having a minus 1 nanocoulomb. Here I am having, let's say, minus 10 volts. Here I am having minus 9 volts. Here I am having minus 4.5 volts. You want to bring a, let's say, plus 1 coulomb of charge from where to where? Infinity to these points. You want to move plus 1 coulomb of charge from infinity to this point. What is the work done? Minus 4.5 joules. You want to bring a plus 1 coulomb of charge from infinity to this point. What is the work done? Minus 9 joules. You want to bring plus 1 coulomb of charge from infinity to this point. What is the work done? Minus 10 joules. Sorry, minus 10 joules. You agree with that? So I told you, potential is basically what? Either work or energy. Of course, work is a form of energy. So final conclusion. If you are having positive charge, near the positive charge we will have high potential. Away from the positive charge we will have low potential. Whereas if you are having a negative charge, near the negative charge you will have low potential. Away from the negative charge you will have high potential. Right? And at infinity, potential is how many volts? 0 volts. Right? Because minus 9 is smaller, minus 4.5 is bigger. If I take 0, 0 is bigger than minus 4.5. So 0 volts is bigger than the voltage here, 0 volts is bigger than the potential here. You agree with that? And this is what we need to remember. Right? I hope you have